All right, good morning. So we'll start with lecture number 5 today. We'll continue from last time. We'll talk about classifiers and one additional classifier this time, which is going to be neural networks. And once we are done with that, we will go and discuss the performance evaluation metrics, specifically for classification. Hopefully you've seen homework number 2 that was released. There's a couple questions, one question on Bayes theorem, Bayes rule, naive Bayes, then another one on logistic regression, another one that connects between the two, one on support vector machines, and another one we have about like performance evaluation metrics, which we have not yet discussed. So I'm hoping that by today we will finish that. So everything that you'll need to do for homework number 2 is already available within the lecture slides. The homework number 1 is due this Friday, 26 Jan. I believe it's at 8 p.m. For distance learning students, it is going to be there on Monday. So you should be able to see it on Canvas when it is when the deadlines are. Homework number 2 was released last Monday, sometime in the afternoon, I believe. And you'll again have around 2 weeks, so until the end of next Friday. Just as a reminder, this is the only 2 homeworks where there'll be an overlap. So currently both homework 1 and homework 2 are online, and you should be able to access both of them. In all other cases, usually we'll finish homework number 2 and then we'll start with homework number 3. That is how we will design the other homeworks. All right, so for today's outline, we'll just talk about ANNs, which are artificial neural networks, and start the performance evaluation part for this particular chapter. Last Monday we ended with support vector machines. And before that, last week we had discussed logistic regression and k-nearest neighbors. So technically we have covered about 4 of these classifiers. As I mentioned last Monday, decision trees, we are not going to cover decision trees. I think there's going to be too much if we decide to go through all classifiers. So decision trees is not something that we are going to talk about. Finally, we will discuss about neural networks today. So this is a table we had seen last time as well. So I'll just go through some very basics of this table just as to differentiate between everything that we have studied, specifically for SVMs. So we made no assumptions on the feature distance. For instance, the only place where this exists is on the conditional independence, right, for naive Bayes. So we never said anything about the features within SVMs. They could be anything that is either learned or something that we would have defined. And we don't need to actually make them conditionally independent or anything like that. There's no assumptions on the feature distribution. Feature normalization, support vector machines, we do require some kind of a feature normalization. In any linear classifiers, this is generally true because we don't want particular features to be overtly represented in our decision boundaries. So we want to make sure that everything is as normalized as possible. The cost function, there's multiple cost functions that we can use. If you go through the lecture slides, you'll see that there's a hinge loss function, which is a convex loss that we are using. In terms of regularization, we did have a lambda parameter that was, actually it was I think an eta parameter that was controlled by capital C, where that was a regularization term. You will see the effect of regularization in the homeworks. What happens based on if you give a large amount of regularization versus a small amount of regularization. Usually we use this in the soft margin classifiers when we know that it's not possible to completely learn separable decision boundary between within our data set. It was a linear classifier, so support vector machines by definition are linear classifiers, but we can convert them into nonlinear classifiers by having this thing called a kernel as a pre-processing unit. So essentially our kernels that we saw was either a polynomial kernel or a radial basis function. So all these kernels, what they do, they act as these kind of transforms where they take your data point and transform into a representation space where maybe the data is now separable in a linear fashion. So they kind of add dimensions to your data so that once you go into a higher dimensional space, you can define a classifier, a linear classifier that is sufficient enough to linearly separate these classes. So we didn't take any probabilistic approach towards understanding support vector machines, and our support vector machines themselves are discriminative. In other words, they don't learn the generative property, they don't learn the distribution of the data itself. Rather, they're only interested in finding a decision boundary between the data. It is a parametric model because we had this W and B, the weights and biases that we learned. So any model, any network, or any classifier with these W and B that you learn are parametric models. Overfitting, it's written not often here, but generally it actually completely dependent on how good your data set is and the regularization term that you're using. Again, we'll have a completely different part of the lectures that is dedicated to what overfitting actually is, along with the regularization aspect as well, and we'll see a connection between the two things. With that, we will move to the next classifier, the last classifier that we will be discussing, which is going to be neural networks. So we'll, going back to what we had done with logistic regression, I think at the time I mentioned that we talked about logistic regression now, but we'll bring it back later on as well. We'll do a very similar thing with neural networks. So currently we'll have an overall perspective, like the base functionality of a neural network, we're going to take a look at it. And we will bring this back later on, somewhere at the end of February, and discuss in depth into deep learning architectures and neural networks and so on. But what we'll be doing today is giving a very basic overview of neural networks themselves. So this is everything that we are going to cover: activation functions, perceptron networks, multi-layer artificial neural networks, and we learn the way that we're going to train neural networks, which is going to be backpropagation algorithm and gradient descent. And at the very end, there's a couple of slides that shows you how we can do something like image classification using these neural networks, but we'll come back to that later during the course. All right. So the idea of neural networks is not something new. You might have started hearing about it somewhere in the early 2010s, but ideally neural networks was constructed much before, during the 1960s. And the inspiration for neural networks are artificial neural networks are biological neurons. Neurons essentially are something that exists in our brains. So the way we communicate, the way neurons communicate between your sensory systems and your modular brain is essentially through neurons. And there are a lot of processes that exist within the human body that helps us achieve this kind of communication. So the most important part that we are interested in from a computational perspective, because again, we want to take this in order to construct a classifier, is the computational part of it. So there's going to be these kind of incoming signals that come in. You can think of it as, I don't know, like touch or your vision. Vision system is probably easier to understand. You have signals that are coming in from the outside world onto your eyes, essentially. And this is the incoming signals. So what happens within this, when you get the signals, is there's going to be some kind of a computation within the human visual system. And that computation is now going to be transmitted to the brain. That happens by these kind of non-linear relationships that exist within the neurons themselves. Now, we're not very interested in the biological features of it, but know that there is a big research topic out there where people are trying to replicate the neurons, the functioning of neurons within these neural networks, and one of them is about this idea of spiking. Spiking neural networks are quite big in field of study these days. So again, the thing that we are most interested in from a very simple computational point of view, is this idea of what an artificial neuron is. We are defining this entire thing based on a very simple computation, which is that given this kind of input that comes in, multiple inputs that can come in, my output needs to be a single thing. Right? So I'm looking at this scene right now where there are, there's a large number of you, and maybe pixel is not a right word to use when we talk about human visual system, but it's probably the easiest way to understand it. Like, the scene in front of me has a lot of pixels, and that pixels can be considered as some kind of inputs. I'm using those inputs, weighing them within my human visual system, within my visual system, and trying to process them and communicate them back to the brain. So a very simple thing is happening, which is similar to support vector machines and logistic regression, which is given my input, I'm going to weigh each pixel separately. For instance, the pixel that makes up you versus the pixel that makes up the background wall. It's not as important. The background wall is not as important to me. So the weights that I use on that background wall is going to be very low, versus something like the pixels that make up you, the students in the class. So that is going to be the weights. I'm going to sum them up, very similar to what we were doing in logistic regression and support vector machine. And there's going to be something called an activation function, from which there's going to be, I'm going to get an output. Now, the activation function, the simplest way to understand an activation function is that it is a nonlinear function. And in order to represent the world around me, it's just a simple linear classifier is not sufficient. I won't be able to process the huge amount of information out there based on a simple linear system. And one way to try to understand this activation function is by saying that it adds this non-linearity, that I can convert a linear system into a non-linear system. So consider the first part of this, right? You have multiple weights, you have inputs. All we are doing in this region is some kind of a simple multiplication. So that is just mx plus b. The summation here is, if you think of W transpose x, which is essentially you're just summing up all your weights and all your inputs based on some weights, and you're just adding a bias. So that is the summation value over here, which is a very simple linear process. If I add an activation, it converts it into a nonlinear system, again, based on the activation that we are going to choose. So that's one way of trying to understand activations. And throughout the course, we'll be discussing these activation functions throughout. So your perception on what activation functions actually do might change across the next couple of months. So a single input neuron is just this one computational system here. But when we discuss about artificial neural networks, it's not just a simple one neuron that is creating this kind of a classifier. It's multiple neurons that are stacked next to each other, which is basically what we are going to call layers, and then multiple layers stacked on top of each other. So in this particular system, we have our input layer, which could be your pixels, and we have about 4 neurons that are stacked on top of each other here. And then this is what we would call a single hidden layer. It's hidden because when we think about the system that a person actually sees, we know what the inputs are going in, we know what the outputs are coming out. Anything within, as a user, I'm not expected to know. I don't need to know the exact functioning of my system. And hence, this is going to be hidden. So you have 4 neurons making up a layer, we have 2 hidden layers, and finally we have an output layer from which we get a decision, whether it could be a 1 or it could be a 0, based on if it's a binary classifier system. There's multiple activation functions you can use. Even in logistic regression, right, we had this access to this thing called a sigmoid function, which we were using. We had 1 by 1 plus e to the power minus x was W transpose x plus b in sigmoid in logistic regression with a sigmoid activation function. So it's not the only one. If you looked at the lecture notes in logistic regression, we didn't go through it in the lectures, but there was other extensions of logistic regression where we could use different kinds of functions. We could use a hinge function. I believe there was a soft plus function as well. So all these functions that we were thinking as just a transformation of the input can be considered to be some kind of a activation function within this neural network framework. So sigmoid function, we already know. A tanh function is similar to sigmoid, except it doesn't end at 0. So sigmoid is, the range of it is from 0 to 1. It can take anything from minus infinity to infinity as its input, but then it spits out a number that is always going to be between 0 and 1. Similarly, tanh function takes in the same minus infinity to infinity, but then it can spit out a number between minus 1 and 1. So this could be helpful in those data sets where you have your classes to be minus 1 and 1. Even in SVMs, we wanted our classes to have minus 1 and 1 so as to get that margin definition of the margin. A very important activation functions that is used in almost all deep learning architectures is the ReLU architecture, which is a very simple function, max 0, x. This is also in support vector machines, but I don't think I described it there. It's a very simple function that just takes in these 2 inputs and gives you the maximum of these 2. So look at the function here, the graphical function here. You have, in this particular function, you have x, if that is your input, anything from minus infinity to infinity is always going to be less than 0, right? So the output of your ReLU function is always going to be 0 in this particular case. But anything greater than 0, the ReLU function is just going to do a max of 0 comma x, and if x is greater than 0, then it's going to output that greater than 0 number. Hence you have this linear function that is out here, while everything below that is going to be 0. In other words, again, remember where this function is going to happen. So at every single neuron, you are basically making a decision based on the input I'm getting, which is this summation. If it's less than 0, then that means that the output of it is going to be 0 if I'm using a ReLU activation function. If it's greater than 0, I'm just going to pass it through. The nonlinearity comes in because of the fact that there is this point over here below which it's going to be 0, and after that it's going to be x. There's a different version of ReLU, which is this idea of a leaky ReLU. So because at 0 there is this point where it's hard for something like a gradient descent algorithm to learn these kind of parameters, sometimes what we do is relax this function. Instead of having a very hard and a harsh decision saying that anything less than 0 is going to be a 0, I'm just going to make it a 0. This is an example, but I'm just going to make it like 0.1 x comma x. So there's a small amount of x that leaks through within the ReLU activation, and that becomes leaky ReLU. Of course, there can be other functions as well. Max out, soft plus are other functions that we can use in order to obtain the kind of outputs that we are looking for. Again, all of this is dependent on the data that you're using and the kind of outputs that you are looking for. So let's go through a little bit about the basic computations of this kind of a neural network. We'll start by calling it a perceptron, because the words neural networks are conflated quite a bit with, especially today, with the kind of things that we have, with the kind of things that are out there essentially from an industry point of view. So perceptrons are the words that were used for these kind of algorithms back in the 1960s, and this is how it was looking like. You have your input signal, x, very similar to what we have been looking at, which is you have x with multiple features, xi1 to xip, and then we have some weights associated with a single neuron. In this case, w1 with w11, w12. The first subscript, you'll know in a little bit why we have it as w11 rather than w1, which we have been seeing till now. But then you have this summation, which is a very simple, again, wj1 transpose xi plus bi. It's a very simple linear module that we are looking at over here, which is a summation block, and you're adding some kind of a bias. The difference, of course, compared to logistic regression and SVM is at this particular point, actually not logistic regression, because there also we had the sigmoid function, but essentially we were multiplying it, or we were putting a sigmoid activation function on top of this in order to get the output. So a single output is very similar to logistic regression. If we were using some kind of a linear activation, then that would probably be the simplest kind of a perceptron that we can use instead of a sigmoid or a ReLU. If we are simply using a linear activation function, that is the simplest perceptron algorithm that we can get. So if we do something like that, which is just a linear activation function, then the output is going to be pretty straightforward. We can have two outputs in this case, 1 and a -1, or if it's a binary classification, again, it's a 1 and a 0 in this case. So your weight transpose x plus b. A linear system, if it's greater than or equal to 0, then it's in class 1. If it's less than 0, then it is in class -1. So that's how you can make this kind of a assertion, saying some data point that you're looking at is class 1 or -1. So we have seen this before, and it's nothing more than a simple hyperplane. So in 2 dimensions, you have this kind of a line segment over here, this bold line segment, where we can differentiate between data. 1 and 2, if we have 2 different classes and 2 different data points, it's pretty straightforward to see that we are getting a linear classifier. In SVMs, of course, we had this max margin, and we had these other nice properties for this classifier, but again, we are talking about a perceptron model that was designed in the 1960s. So at that point, we were not yet looking at this kind of max margin algorithms. So this is in 2-dimensional case. In a 3-dimensional case, we can have something similar. this is what you see here on the right-hand side. So you have W1x1, W2x2 plus W3x3. Same thing as W transpose X plus B equal to 0, and you have this kind of 3-input perceptron model. So how do you learn this kind of an algorithm? Till this point, we have looked at two ways of learning. One was gradient descent, and the other one was the Lagrange duality. So the gradient descent is what we saw in the logistic regression part, while Lagrange duality was something that we saw during SVMs. Perceptron has its own learning algorithm, which is very simple. When we come to later part of the this class, we'll discuss about backpropagation, which is a bit harder, but essentially it's very similar. So what we do is we start off with an initial set of weights. It could be random. We take an initial set of weights that are going to be random, and we'll start calculating the outputs and inputs. So in this case, for a single neuron, right? Our output is going to be y sigma W transpose X plus B. Hopefully, again, this is not something that is new. Logistic regression had the same thing. The way we are going to update the weights is by this WIT plus 1 equals WIT plus alpha XIT ET. So let's go through and look at each of the terminologies in this equation. E is your error function. So let's say I have my class as 1 for a particular data point, but my perceptron algorithm is giving it to be a 0. In other words, it's misclassifying my input. In that case, the error, you can define an error function, which is going to be something, if it's a very simple error function, let's say it's just a subtraction between the two, 1 minus 0 is going to be my error function, right? So in this case, if the class is 1, our prediction is 0, the error is just 1. So it's just a difference between calculated output and desired output. And then we'll define something called a learning rate, alpha. Again, at the end of this class, we'll discuss about how we can derive alpha, but for now, not derive alpha, but set alpha at least. But for now, we can discuss, we can take it as some kind of a constant that is less than 1. You'll see this value t quite a few times. T is essentially my iteration. So it's not that there's a closed form solution for this kind of an equation, especially when we have different kind of activations. There's no closed form simple solution. So what we have to do is train it across iterations, train it across epochs, and that is the value t you see at this point. So in the beginning, you'll start off with random weights, right? So wi of 0 is going to be something random, but at the next iteration, which is wi1, you'll have a specific way of obtaining or changing your weights based on your error function over here. So wi of 1 is wi0 plus alpha xi of 0 e0. So you'll get some error function based on the fact that you look at what your output is, and then you also have your x, and based on that, you can make some changes to your w, and it keeps on changing. We'll see in a little bit, especially when we discuss gradient descent, how that change actually occurs, or an intelligent way, more intelligent way in order to make those kind of changes. But essentially, the important part here is to think of it as a set of iterations that we will be updating our parameters, and that parameter in this case is w. Again, b is not given here, like we haven't put bias, but it's bit plus 1 equals bit plus, maybe in this case it's going to be beta xi of t e of t. So bias has its own function in order to update itself as well. So what was the problem with, yes?
On the last equation there, when we see e to the t in a machine learning context, should we think like the difference between calculated output and desired output, or will we also see it as Euler's number?
No, it's so let me repeat the question for the online students. So the question is, when we see E in a machine learning context, what does it usually refer to? The answer is that it's always an error function. It depends on which case you're seeing. So if you are looking at a sigmoid function, for instance, 1 by 1 plus e power x, in that case is going to be a ln function, but usually we represent it using sigma. We never go through and say it's 1 by 1 plus e power x. We usually represent it as a sigma, which is shorthand for the entire thing. So we never go in with the assumption that E gives us the ln or Euler's number. It's almost always going to be error function. But it's a good question because later on we never use E as error because we'll use something called loss function, L. And we have seen that in logistic regression. It kind of means the same thing. Error is just a very simplistic form of a loss function that we can use.
And also here, what's the difference between, so the W is weights, but what's the X in this?
The question is what X is. X is just your inputs. So if I were to go back at this point, it's your input signal. So anything where you have features is going to be your input signal, which is X. Any questions? Other questions? All right. So this perceptron was discovered, or maybe not discovered. It was known. We knew about perceptrons back in the 1960s, but then there was a big problem with the idea of perceptrons, and that was that XOR function, the logic gates for XOR, is not something that could be easily represented using a perceptron. Again, SVM, we have already seen how to take care of this. We'll just have a simple kernel that does it. But again, SVMs was in the 1980s and 90s. In the 1960s, this kind of an XOR system was a huge problem, which is that given these 2 points, 1 and 1, at these 2 locations, the data is not separable using a simple linear classifier, right? So look at the right-hand side for this logic gate. So when it's 0, 0, you have output 0, 0, 1, output 1, 1, 0, 1, and 1, 1, 0. Our goal is now to separate this particular data. But it's not linearly separable. So there's no way using a simple perceptron algorithm we'll be able to differentiate this data and find the solution or implement XOR gates using a perceptron algorithm. So how do we go about trying to change our perceptron in order to not just perceptron, but SLP, which is single layer perceptron? How do we change your single layer perceptron in order to be able to solve this XOR problem? The answer is some kind of a hidden two things. One is we need a nonlinear activation, and the other one is a multi-layer perceptron. So it's not just a single perceptron, but there's this kind of a hidden layer that can exist where we'll be able to differentiate this separable data. So let's start by looking at the calculations that will help us to try to finally ultimately understand neural networks. Let's say that this is my network over here. At the bottom, this is going to be my network. In this network, I have 2 inputs, which is x1 and x2, and I have one output, which is y, and there is one layer, hidden layer here, which is h1 and h2. So when I say we have one hidden layer and I say h1, h2, we have 2 neurons within one hidden layer. That's what I mean by that statement. So let's start by saying that I'm giving you some values. I'm giving you WH1 is 20 and 20, and WH2 is minus 20 and minus 20. In other words, the blue line segments here, each of them, the weight of those blue line segments is going to be 20 and 20. The golden ones are going to be minus 20 and minus 20. That is what this WH1 and WH2 is giving me. And then I also have WY and BY, because at the end we have the output neuron as well, and that layer has its own weight functions. So it's going to be WY is 20, 20, and there's a bias of minus 30 attached to it, right? So yes, question?
Same, like for H1 is 20 and 20, but and then for H2 is negative 20.
So the question here is why WH1 and WH2 have the same numerical values but different signs. This is just a made-up scenario, just so that's to make it easy to understand the calculation in the next one. It's never going to be the same. In real-world scenarios, if you ever find that something is 20 and 20, that means you have done some mistake within the learning framework, because that means it started off in a random fashion, it has remained in that random fashion. So this is just a toy example to get to the calculation part.
Both of them are, the weights are 20, but will the weights always be the same for each hidden layer, or?
No, it's not going to be the same. It's going to be always going to be different. So the calculation that we are going to get is shown here. So BH1 is minus, so BH1, BH2 are the 2 things here. Out H1, which is going to be just the output of H1 is the same linear classifier, which is W transpose X plus B with a sigmoid activation function. So we are using a sigmoid activation function in this case. So 20x1 plus 20x2 minus 10 is W transpose X plus B. B is minus 10 here, that's why you have minus 10, and then 20, 20 are the two weights. So hopefully this calculation is clear. And then sigmoid activation, sigmoid function is sigma x, which is 1 by 1 plus e power minus x. So based on this framework, let's try to actually solve the XOR solution. Again, XOR not possible using a single neuron. But the assertion right now is that given two things, which is the nonlinear activation and a hidden layer, we will be able to solve XOR, which is given input 0 and 0, I'll get an output that is 0. Given input 0 and 1, I can get an output that is 1. Given inputs 1 and 1, I can get an output that is 0. Let's start by looking at the first one. So input 0, 0. If you put it into, if you use that as an input for H1 as the output of H1, you have sigma 20 multiplied with 0 plus 20 multiplied with 0 minus 10, right? Because two weights are 20, 20 are the weights that are going into this neuron, and the bias is minus 10. So what you'll see is 20 plus 0 minus 10 is minus 10. And if you put this within a sigmoid function, this is a representative sigmoid image on the right hand side, minus 10 almost approximates 0. So you have 0 as the output of your H1 neuron here. If I do the same thing for H2 neuron, which is here on the right hand side, maybe I should have had a separating something here, but H2 is this neuron over here, the middle portion, sigma minus 20 into 0, minus 20 into 0 plus 30. Right, so this 0 into 0 plus 30, and if you look at the sigmoid activation, it's going to be 30 x-axis. In the y-axis, it is 1. So essentially, that means you're getting 1 as your output from H2. From H1, it was 0. So for 0, 0, the output from H1 is 0, and the output from H2 is 1. Is that clear? All right, so now these two are, you already have the outputs of H1 and H2, but the outputs of H1 and H2 are stacked onto the output layer, right? So they are now the inputs to the final layer here, which is Y. So now you need to calculate the Y, and Y again is similar, sigma Y multiplied by 20 H1 plus 20 H2 minus 30, because the bias here is minus 30, and the weights are 20 and 20. Right, so when now let's put that into the first case. We already know H1 is going to be a 0. We already know H2 is going to be 1. So 20 times 0 plus 20 times 1 minus 30, which is going to be 20 minus 30, which is minus 10. And if you look at the x-axis in minus 10, and the corresponding y-axis will give you almost 0. So the output is going to be 0. So output of 0, 0 gives me an output of 0. Is this clear? Everything we have done, question, yes?
Function for like H1, H2, and Y?
Yes. The question is what the activation function is for H1, H2, Y. For this case, we do use the same sigmoid function. And even in any large-scale neural networks, usually when you set an activation function in the beginning, you use that throughout every single neurons that exist within the framework. Even if you have a billion neurons or trillions of neurons in your network, it is usually going to be the same activation repeated over and over again. Yes?
Why is this a nonlinear activation function?
Could you repeat that, sorry?
Why is it a nonlinear activation function?
So linear activation function, so the question is why is sigmoid a nonlinear activation function? A linear activation function is given, simply put, if you just look at the graph, it's not going to have this kind of a nonlinear region. So at every single point, it's going to have some linearity. The simplest thing is a 45-degree line. Given x equals 30, my output y is also would have been 30. But in this particular case, given x equals 30, my y is going to be almost 1. Given x equals 500, my y is also going to be almost 1. So it's not linear because of the fact that with the linear change in input, there's not going to be a linear change in my output. So that is the definition of linearity in this case. 45-degree one line was a very simple way of expressing it. You could have a minus 0, you could have a 0.1 into x. That would also be linear because, but you know, it's that 500 multiplied by x multiplied by 0.1 would give you a 50. But still, the change would still be linear in that case. Any other questions? So let's do the same thing with another input, which is going to be 1, 1. So from h1, my inputs are 1 and 1. So 20 multiplied by with 1, 20 multiplied with 1, and minus 10, which is bias. 40 minus 10, which gives me 30. If you look at the sigmoid function, 30 is almost a 1, which I'm going to take. Then let's look at the outputs from h2. Minus 20 into 1, minus 20 into 1 plus 30, which is minus 10. Minus 10 after you pass it through sigmoid is almost 0. So the inputs into my output layer is going to be 1 and 0. 20 times 1 plus 20 times 0 minus 30 is going to be minus 10, which also, if you pass it through sigmoid, is going to give me 0. So given I input 0, 0, I had a 0. Now given input 1 and 1, I'll also have a 0. So two factors within my XOR system are now satisfied, which is the top one here and the bottom one over here. You can do the exact same analysis for 0 and 1. So in this case, 0 and 1 are the inputs to my H1, H2 systems. So 20 times 0 plus 20 times 1 minus 10 will give you a 1. Minus 20 times 0 minus 20 plus 30 is going to give me 10, which look on the sigmoid, it's 1. So the inputs into my output, my final layer is 1, 1. 20 times 1 plus 20 times 1 minus 30 is a 10. Which gives you 1 as your output when you pass it through sigmoid. So the same thing happens when you have input of 1, 0 as well. So look at the input 0, 0, 1, 1, 0, 1, 1, 0, and look at the outputs. It's 0, 0, 1, 1, which matches exactly what you wanted from the XOR table that you have over here. Yes? I'm not sure. Oh, so it falls here, you mean? So the question is, this is an exaggerated example where most of the results were in the minus 20, minus 10, minus 30, 30 range. But now the question is, okay, maybe if the values fell somewhere between minus 5 and 5, what would happen? Right? Then that would mean that you would have to change your weights. So this is when the backpropagation and error comes into picture. You don't want your outputs to be somewhere in the middle. You either want it to be 1 or you want it to be 0, right? If you look at the outputs here, there's no 0.5 that exists. There could be, we will see examples where this is not just 0 and 1, it's not just a binary classifier, it'll be a multi-class and there's a regression module there. But essentially, when it's this kind of a classifier, that means your weight has not been learned properly. So you look at the error and you would have to go back and say that maybe 2020 is not the right weights here. Maybe it's an 18 and a 17, or maybe it's a 19 and a 25, something like that. So you need to change your weights in order to make sure that your output is going to be correct. Any other questions? All right, if not, then we have found our decision boundary, not just as a single line, which is mx plus c, which we were doing in logistic regression and in SVM, but rather as this complicated set. Actually, it may not be very complicated, but just a lot of computation is happening in order to find this decision boundary to do an XOR problem. So what are the benefits of hidden layers? Any bounded continuous function can be represented using hidden layers. Any Boolean function can be represented using hidden layers. Boolean function is a 0, 1. Continuous function is something that can exist between 0 and 1. So 0.12, 0.113, 0.1449, anything. Any function like that can be represented using hidden layer. Also, zeros and ones can also be represented using hidden layers. What we saw was a single hidden layer. But now you can start thinking, okay, I can stack one on top of the other. XOR seemed a very difficult problem back in the 1960s and stopped the research into perceptron, but now we know that addition of hidden layers is very helpful. And since then, we have done a lot of things with neural networks, right? The current generative AI, everything that you see with DALL-E or ChatGPT is based on these very simple modules. But it's not based on a single layer or just 4 neurons stacked on one another. It's like trillions of parameters. GPT-4 has 1.7 trillion parameters, and it's not like all of them exist in a single layer. They're stacked in multiple layers within your networks that exists. So there's this kind of a layer-wise organization that we see. In this case, what you're seeing here on the right-hand side is something called a fully connected layers. That basically means that every question?
Yeah, so you said that, like, for example, for ChatGPT, it's like stacks of layers.
Mm-hmm.
At what point do you decide to like stop layering?
That's a good question. So the question is, we can have multiple layers in a neural network. At what point is something sufficient? So the answer to that is not very simple at all. When we discuss neural networks and say that it's a black box architecture, this is exactly what we mean. Sometimes before you start working on it, it's very hard to say that 3 layers are sufficient to do something, or 4 layers are sufficient to do something. That brings in this idea of capacity. So there is this research topic called capacity of neural networks, or capacity of models, where it should be able to represent everything within your data set. If it's very simple Boolean functions like this, you don't need anything more than 1. But when we are looking at the world around us, like the images, the videos, it's not easy to say that just using these X number of modules or layers, we'll be able to find the answer. We have to design a capacity module that looks at the data set and says that the minimum capacity required in my network is this number of bits, let's say. So then you need to say that now the network has to be able to represent this number of bits. So then you can say, okay, maybe I need the width has to be in each layer, it has to be 10, and then there have to be 4 stacks of these neurons. Or you can say that there can be 5, but then you need 20 stacks, 20 layers of neurons. So you need to, it's a research question. There's no solved solution for something like that. Yeah. All right. So in this particular thing now, we don't have SLPs. We have something called MLPs, which are multi-layer perceptrons. So in this particular case, we have about, network has 10 neurons, 4 here, 4 in the first layer, 4 in the second layer, and 2 in the output layer. And the number of weights is going to be 4 multiplied by 3 in the first layer, 4 multiplied by 4 in the second layer, and 4 multiplied by 2 in the third layer. It's essentially just the number of parameters, the weight parameters that exist. So even in this small framework, you see that there are 36 weights and 10 biases, right? So that means there are 46 learnable parameters. So when I said that GPT-4 has 1.76 trillion parameters, think of the number, the size of the model itself that OpenAI had to train in order to solve not solve, but at least find one solution for the task of natural language processing. So whenever we discuss that a network is very big, there's a lot of parameters, all we are saying is that these learnable parameters, the weights and biases, the same things exist over there as well, except now it's at very, very, very large scale. It's almost, it's very difficult to fathom as well what 1.76 trillion parameters actually looks like. But it's still the same thing. It's number of weights and biases that are just stacked on top of each other. So let's talk very quickly about learning these set of parameters. When we discussed the update rule for perceptrons, it was very simple. WT plus 1 equals WT plus some alpha multiplied with x into the error function. But and we said that when you finish doing this across n number of epochs or iterations, you will be able to learn a particular set of parameters that is sufficient for a perceptron. But in this case, it's not sufficient. Just doing something very simply for a SLP is not sufficient when you have multiple hidden layers and you have activation functions that are there. You need something called gradient descent. Again, gradient descent is something that we saw last time in logistic regression, but we had not gone through the exact details, which we are going to do this particular in this lecture. The idea of gradient descent is very simple. If I have a 2-parameter network, which is shown here. Let's say you have, or I guess in this case, if I have a single parameter network, all I need to do is learn theta. I'm going to represent that theta on the x-axis, and I'm going to create a loss function. Before we thought of it as error, but I'm going to create a loss function, something like a negative log likelihood, let's say, or something like cross entropy. And I'm going to represent that on my y-axis. The goal for me is to find the minimum possible loss given some parameter. And that some parameter is the best possible parameter that I can learn. Usually, this kind of loss functions, we choose our loss functions to have this kind of a shape, what we call convex functions. We want this kind of a shape because there is this kind of a optimal minima that we'll be able to learn using a procedure called gradient descent. Whenever we see these kind of plots, essentially x-axis is always going to be these parameters. Now, if I had two parameters to learn, W1 and W2, you'll think of this as a three-dimensional block, right? So then this is going to be, rather than just a simple parabola, it's going to be a bowl shape something, where our goal is to get to the bottom of that bowl. If there's three parameters, it's not possible to visualize it like this, because then if you have a loss function as well, that would be a fourth dimension. And the human brain, we are incapable of visualizing or trying to understand from a visual perspective. In that case, what we usually do is we take theta to be a vector of parameters, right? So if it's 50 dimensions, let's say, in the previous example, we had 46 learnable parameters. So ideally, in order to represent this kind of a graph, I need a 47-dimensional plot where I'll be able to draw this kind of bowl or parabola or whatever it is called in that hypersphere, essentially. And to get to the minima of that, I would have to do gradient descent. But to visualize it, I would require a 47 dimensional space. But since that's not possible, usually what we do is we take the 46 parameters and put it into a single vector. And that theta is usually what is represented. And every point is a neural network, is a 46 learnable parameter thing. In a 47-dimensional space, this is going to be a point, right? So think of that exactly like that in this two-dimensional space itself. The 46 parameters, I'm taking it as a vector, and this point here is the worst possible neural network. The random neural network that you started off with is this point here. I move a small amount and change my weights in a way we'll talk about in a bit, but then the loss function has decreased. So this point here is another neural network with a different set of parameters, with a different set of 46 parameters that we have. That is essentially what you're seeing in this graph. It's a little bit hard to take that in, maybe in the beginning, but once you start seeing these plots, once you start doing it on your own in the homeworks, hopefully it is going to become clearer. But you need to have that kind of a visualization thing where you start thinking of each point not as just a parabolic point, but rather as neural network parameters, as a neural network by itself. And the goal is to get to the best set of parameters or the best neural network that will give me the least amount of the least amount of error. Any questions? Yes.
Look at the local minimum.
What if you're stuck at the local minimum? Good question. So in this case, we have a very idealized scenario, which is this kind of a global minima is the same as the local minima. There are a number of optimization ways in which we can use to get out of local minima in order to find the global minima. So one way to do it is we discussed about these iterations, right? So if I keep on doing this kind of a descent algorithm, and I'll see across 20 iterations, nothing has changed. So what I can do is go back 20 times before what it was and choose a different step length. That alpha parameter that we just said was a constant, you can actually schedule it. You can say that until about this point, you can have a 0.1 as a parameter, and then I can have a 0.05, let's say. Maybe 0.1 was very large, and I need to get out of the local minima, or maybe 0.1 was very small, and I need to go inside the local minima a little bit more, in which case I'll make it like 0.01, 0.001. So step step length is one way. Another way is gradient descent, maybe not the right algorithm in that case. There's other methods like Newton methods, second order gradient based methods that you can use. But usually in neural networks, it's very hard to, it's computationally very expensive. Again, we're talking about billions of parameters, right? It's computationally very expensive to do those things. So usually learning rates, and there's these other hyperparameters that we can define in order to get to say. Yes. So the question is the most difficult part designing the loss function? Actually, it depends on the data that we are looking at, but I would generally say that a majority of cases, the kind of loss functions that you use need to be as simple as possible. It could be a simple mean square error, or it could be the cross entropy, which is just an expansion of the negative log likelihood. Simple loss functions are usually the ones that yield the best results. The reason being that you don't want to, you want to have a simple convex function as your loss. Maybe there is data where you'll never be able to have that kind of a convex function, but in a 50-dimensional space, something that is very impossible for us to represent, like a non-convex loss, can become a convex function over there. So the answer to your question is, as long as we are choosing some kind of a convex loss, we should be fine, because there's a lot of optimization algorithms that we have designed in order to get to a spot where we can get the minima. The problem becomes when this minima is either a local minima or a saddle point, and for that, there's different optimization functions that are designed for that case. Yes?
Why are we able to use the loss function in the first place? Like, I thought it's like the difference between our prediction. So like, yeah.
So the question is, why are we able to choose the loss function? The answer is that the simplest loss function is a subtraction, which is the error function, right? But if you look at the definition of what that is, it's not just a subtraction. From a distance point of view, it's something called Manhattan distance, where it's an L1 loss. And then you can have a squared loss, right? So let's say that it's hard without showing the... So let's say I have something like this. I have 2 points. This is my predicted point, and this is my actual point that I need to get to. Now, the distance between these two things is dependent on the manifold that they are going to reside on. And those words I know might not make too much sense. In other words, what I'll tell you is, I'll give you a constraint. I'll tell you that the only way you can get to these points is by moving in 90-degree directions. So you take this, you go like 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 this, right? Whenever you do some subtraction, you're actually getting this result. You're moving in very small steps, in very tiny steps, in order to get to this stage. But maybe there's an L1 loss function, L2 function, where I can directly go from here to here, and this is like something called an L2 loss function, where the manifold is essentially curved. So I can go through this curved space into this thing. Now, you can define other kind of loss functions. Let's say L0.5 loss function, where the only way to go from this point to this point is something like this. At the top over here. This depends on how much I value the distance from here to here. Because sometimes what happens is that in this representation space, I have, I don't think yellow works well, maybe black. I have another data point here, and in this representation space, I want to make sure that the distance between these 2 points is actually more compared to this and this point. So I want to design a representation space, which is exactly what you do when you choose your loss functions. So the simplest way is, of course, the L1 loss function, which is the error, but generally we don't do that. In logistic regression, if you remember, we had that log loss. So we wanted to penalize certain portions more than the other portions. So that is exactly what I mean by saying that I want this distance to be more than this distance. I want to penalize this particular distance more than the other. That is when you start designing your loss functions or choosing your loss functions that best describes your application or data. Yes?
Is it also always as easy to, like, with the one-to-one mapping, because you're talking about having predictions and like desired output?
Yes.
So like, how difficult can that, like, could you have like multiple like desired outputs for like a particular input, and like how do you deal with that, like using like a loss function?
Good question. So the question is that when it's a one-to-one mapping between the input and output, it seems fairly straightforward. But what if there's a many-to-one mapping? For instance, you have the category as a dog, but then there can be millions of dogs that can exist, and in different poses, in different backgrounds, in different shapes. In that case, it's not a simple problem at all. That's why we have millions, billions, and trillions of parameters in order to handle all those cases. We have to extract certain features. So in this case, we are just we haven't even talked about what X is, right? So we are just saying that some features. But in general, for neural networks at least, we cannot hand design features for all million dogs out there. We have to let the network itself design its features. So our inputs will just be images, a million images, let's say. So it's not simple at all, but it is possible. And there's things that you need to do: the size of your network, the loss function, the optimization algorithm, the way you're inferring, everything has to change based on the parameters that you design for your problem. All right, so the way we do this is via something called gradient descent, and an expanded version of gradient descent. This is something that we saw in logistic regression, which is given weight parameters, we can now construct very simple, this kind of a loss manifold, which is your convex function. Across steps, we can move to the minimum loss. In this case, how many steps are there? 1, 2, 3, 4, 5, 6. So across 3 iterations, your yellow dots will keep moving towards this particular point. Your loss function in this case is a tangent to this curve. And this loss function, gradient is a tangent to this loss curve. And by making use of this gradient, I can move down to the bottom of this convex function, which is where the best parameters will reside. Now, another slide about just review of derivatives. So I'll come back to this slide in a couple more slides afterwards. But essentially, derivative gives you this kind of a direction which has the most amount of loss. So you have your L of theta, dou L by dou theta, which is the derivative of your loss function with respect to the parameter. Ideally, you want your gradient to show the maximum change in loss with some change in theta parameters. So there's multiple ways, right? So if there's 46 parameters, I can change 2 of these parameters, I can change 3 of these parameters, or there's so many combinations that I can make small changes in. The best choice that I can make is the one that shows me the highest loss function. So I want the maximum amount of loss, the parameters that make changes to the maximum amount of loss in order to get to this minimum loss in the fastest way possible, in the most intelligent way possible. And that's done using these kind of gradients. There's some aspects about gradient descent and gradients in general, one of which is something called chain rule. So if I chain 2 functions together, f and g of theta, if I now differentiate dou by dou theta of f and g theta, chain rule essentially says that you need to differentiate the entire algorithm, or not algorithm, sorry, in this case 2 functions, and then with theta, and then go inside and differentiate the second function. So in this case, it's going to be dou by dou g of the entire cascaded functions, which is f g of theta, multiplied by dou theta with g of theta. So this is essentially our chain rule. For sigmoid function, which is dou by dou x 1 plus e to the power of minus x inverse, the derivative is given by this sigma x into 1 minus sigma of x. If this whole thing is sigma, then the derivative of sigma is the one here that you see on the right hand side. We'll be utilizing these things. Again, this is more of a review of derivatives rather than going and learning about what derivatives actually are. So we'll be using these 2 facts in the next couple of slides. Some terminologies. When we say that we give an input and a network, it passes through the network to give us some output, we are saying that it's something called a forward propagation. And when we say that given this particular input, we'll get some kind of a loss function, it's called a backward propagation. Whenever we have a loss function and we are updating our weights based on that loss function, it is called backward propagation. So these are the two terminologies. When we think of feed-forward input, we think of your X, which is your inputs, some weights, and the neuron themselves have two things happening within. One is just a simple linear summation, and the next one is this kind of a transfer function or an activation function. In this next couple slides, we'll look at that as a sigmoid function, but again, it could be any kind of an activation function, as long as it has a defined derivative, which we'll talk about in a little bit. In backward propagation, we do the same thing. You have some error or a loss function that goes back through the activation function again, through the summation, and back into the input. This is what happens in a backward propagation. All right, so let's start looking at this algorithm called backward propagation, backpropagation. This is one way, or this is the way designed to learn these number of, again, we have so many parameters, right? Maybe trillions of parameters. Our goal is to learn given some amount of data. And the algorithm used is backpropagation. I think this was published back in 1980s. At that time, it was for a very simple multi-layer perceptron, but the same thing we are using now to train all the new architectures. Everything that you see online today is all based on backpropagation, based on this very simple gradient descent algorithm. So we start off with a sample, which is X. Let me find my cursor. Okay, it's here. So we'll start off with this new sample, which is going to be X, has about n different features. In this case, we are seeing it as 3 inputs, but it can be n number of inputs. We start by forward propagating this input through the network. Let's take this as an example, the G1 to Gj as an example within our full framework. This is the hidden layer that we'll be looking at. Gj is given by sigma bj of 0 plus sigma k uj of k multiplied with f of k. Right? So this is a very simple what is happening within the sigmoid function. You have your linear classifier, or I shouldn't say classifier, you have your linear function multiplied with or input into this kind of a activation function, which is nonlinear. Finally, you'll predict y as y star, and we'll start by taking some kind of an error or a loss function here. In this case, again, let's just assume it's very simple, y minus y star, which is going to be our output and our input, and we get some kind of an error. Our goal is to obtain G1 to Gj, which is we want to obtain the parameters that lead into all these things. We want to get uj of k, we want to get vij, we want to get wi, tkm. All these parameters that exist, we need some value associated with them. In the beginning, we start with some random values, but we need different values, right? And for that, we can think of it as some kind of a, in this slide, it's more of an intuition rather than the algorithm itself. So what we need to do is we need to determine whether this Gj has to be higher or lower. Right? If you go back to that 2020 example that we had, one of the questions was, what if the output of that was something like 0.5, 0.7? And the answer I gave at the time was that maybe our weights are incorrect. Maybe we need to change our weights in order to get to a stage where the sigmoid activation gives me a good result. And that is exactly what we need to do here. We need to see if Gj, the output from Gj, has to be low or high, and make adjustments to the input parameters ujk. If this were 20, then we need to maybe decrease it, or we need to increase it in order to get to a stage where our outputs is sufficient. And that is essentially what we'll be doing, or what backpropagation tries to do within this entire framework. So we need to determine whether these nodes are giving you good results, and if they're not, then we need to update the weights. So in this case, we are looking at this layer, so we need to update uj of k based on some function. Since we'll be using gradient descent, it's based on this dou e by dou g, or dou e by dou e. We'll start thinking of this very complicated looking sigma dash hi wij, it's actually nothing more than a scalar, because remember, we are looking at as an equation right now, but when we did the calculations, we got a 20 or a 30 or a minus 10. So all these are essentially scalars. And since this is not dependent on u, it is not going to depend, the derivative of that is going to be 0. Right? So it's, in this case, we'll start thinking of it as a scalar. And the reason this makes sense is the way chain rule is designed is that we don't need to look at this as 4 layers stacked on one on top of the other. We can start looking at it as separate 4 things that we can update, separate 4 layers that we can change, and that change will be reflected in the previous one, but that doesn't matter, because when I make changes to wi over here, I really don't care what else is happening in the previous thing. All I'm going to do is just look at this weights as a single layer, which is very similar to what we did before. So intuitively, what gradient descent and what backpropagation algorithm is telling us is that you can think of, you can be very greedy when you are backpropagating these algorithms. Any error that you get from y minus star, use everything, use all of that error to update weights wi. And then see that with those changes, your h1 to h3, maybe now that needs to change, right? Use the error from h1 to h3 in order to increase or decrease vi of j. So you can create this kind of a greedy algorithm where you have one error, which is y minus y star at the very end. Then you can have multiple errors in the middle. And you can start using these errors to backpropagate one layer and say that I need to update my weights, and go one layer back and say I need to update these weights, and so on. In fact, the algorithm itself is called like a greedy search algorithm, because every error that we find, we'll just use it. As soon as we find an error, we'll use it within a certain layer. So let's start looking at the actual calculations that exists. Let's start with the final one. So E is equal to half y minus y star whole square. So instead of just looking at it as a subtraction, in this case, we are looking at the L2 distance, or the mean square error. You can think of it least, there's different names for that, least squares as well. So your half y minus y star whole square is the error function that we are going to be using. We'll start by differentiating this error. Again, we want to get to a minimum loss function, right? So the best direction is given by the gradient. Dou E by dou H. In other words, I'm going to look at this as a system by itself. It's just a very simple classifier. So given some error, I'm going to differentiate it based on this set here, h1 to h3, these nodes. And this is the output that I get. Dou E by dou H is y minus y star dou y by dou h1, dou hi. So if you differentiate this function, if you differentiate it, it will be 2 into half y minus y star dou y by dou hi, right? So 2 cancels, and you have y minus y star dou y by dou hi as your output in this particular case. Now you might say that maybe dou y by dou hi should be a 0, because in this case you're not seeing any h. And by simple laws of differentiation, whatever you're differentiating by has to be here usually. But y is a function of h. Right? If you look at y equals sigma b naught plus sigma plus summation wi hi. So hi is actually a part of y, and that's why you have this kind of output. Now we know that when there is a sigmoid function that is involved, this thing over here, if I go back to this slide, my output when I differentiate a sigmoid is sigma dash x is sigma x 1 minus sigma x. Right? I use that here as well. I use that thing exactly over here in order to, when I differentiate my sigmoid, I should be able to get the output based on that formula. All I'm doing is just substituting what I just mentioned in the previous slides back into this case. Now, the sum goes away because we are differentiating with respect to one of the elements. The sum that the slides is talking about is this. Sum wi hi, so it's w1 h1 plus w2 h2 plus w3 h3. Right? So it's basically what we are doing is just differentiating by h. So you don't need the sum anymore. The simple wi should give you the result, and that's why you have this simple wi here. Any question in the second equation? Yes.
You differentiate wi hi with respect to hi, right?
Yes.
And you get wi after.
You get what?
You get wi after differentiating.
Yes.
Oh, okay.
So if you look at dou y by, so look at this here. E is this one, but when you do dou e by dou h, you have a dou y by dou h. So I'm going to be differentiating this entire thing. And summation wi hi, when you differentiate hi, all you're left with is a wi. And the other one comes in, y minus y star y into 1 minus y. That comes in because you're differentiating a sigma, which is your activation function. So when you differentiate sigma of x, in this case sigma of x, you get sigma x into 1 minus sigma x. That is what we saw in the previous slide, right? So that I'm just substituting that back over here. That's all that is happening. Now that was with respect to dou h, which is one of my layers. Now I want to differentiate it with more. I want to differentiate it with respect to g in this particular case. So I want to go one step back. And the way I can do it is by literally substituting using the chain rule, right? So dou e by dou g is given by y minus y star dou y by dou g. But I can substitute dou y by dou g based on the chain rule, which is, it's just a cascaded set of functions. F of g of theta, if I go back to this slide again, f of g of theta, the f is the final weights, the wi. The g in this particular case are going to be the u weights, which is, or was it the v, the one after g? Yeah, the v weights. So all we are doing is thinking of it as multiple functions that are stacked one on top of the other in order to get our results. So that's all. This is nothing more than an application of chain rule. And by observing the nesting pattern, which is basically the cascaded functions f and g of theta, we'll start by making some kind of substitutions back into the main equation back again. And the upshot of it, the final thing, is that you can keep on applying this chain rule in order to go to the very end over here and get a final result. It might seem, just by looking at this slide, it might seem very difficult or complicated, but it's not. There'll be a homework problem where you will go through and find the exact results. So when you actually do the computation yourself, it should be much easier to do this. But again, it's really not hard. Everything that you're doing is cascading one on top of the other and then applying the chain rule over it and over again. Based on the fact that you already know that there's a softmax function, and a softmax function has a definite known differential thing, which is sigma x into sigma 1 minus sigma x. All you're doing is just substituting over and over again in order to go from the first part until the very beginning. At every stage, you need to keep updating w's here, v here, u here, and t's. But in all those cases, you'll be updating it based on the fact that there is going to be an error that is going to exist at this spot, error that is going to exist at this spot, and so on. So this is more of a summary. Again, the reason we call it a greedy thing is no nodes know about each other. So if you have Gj here and G1 up top, G1 doesn't know what is happening with Gj. There is a error function that is associated with this particular node. It's going to use only that node in order to update all the weights that are going into that particular node. That is what makes chain rule possible. Not chain rule possible, sorry. That is what makes backpropagation possible, where instead of thinking of this whole system as 46 different parameters, we only start looking at them as a single parameter that is affecting all the w's that are going into that particular node. This is more of a summary, so you can look through that later. Again, this is a summary of what we just discussed as well. Given some x's, you will have, which is your input signal, it can pass through your network to get any number of outputs. We usually think of it as two outputs, which is a binary yes or a no, but it can be any number of outputs. The most popular algorithm that exists in image processing in computer vision, popular data set is ImageNet, and the goal in ImageNet is to classify 1,000 different classes, which means that at the very end, there's going to be 1 to 1,000, y1 to 1,000, y1000, which is what you would have to classify in that case. And the inputs is going to be images, right? So if it's a like a standard image in computer vision algorithms is 224 cross 224 cross 3. So the number of parameters is literally that. Number of input parameters is 224 pixels multiplied by 224 pixels, which is the length and the width of the image, multiplied by 3 channels, which is RGB. So the number of parameters is 224 multiplied by 224 multiplied by 3. I'm not really sure what the output of that is going to be, but that is the number of input signals and parameters that exist. I have no idea what just happened, but maybe this is a good time to end it as well, because that was a summary of backpropagation. So just as a reminder, Friday is the homework due date. So by 8 p.m. Friday, homework 1 has to be submitted. Homework 2 is already out, and hopefully everybody has started taking a look, because homework 2 is significantly more tougher compared to homework number 1, because everything that you have learned with naive Bayes, SVMs and logistic regression is represented there. One thing that we were not able to complete today is the performance metrics, which you have a question in homework 2. We will discuss that on Monday.